In this video, I'm going to go over the Wolff-Kishner reduction, which takes a hydrazone and reduces it down to basically just an alkane. So a hydrazone, draw it a little bit lower so I make sure I have room for everything. The hydrazone, it's a carbon with a double bond to a nitrogen, and then that nitrogen is bonded to a primary amine. So the hydrazone will react with KOH and water to give, in this case, pentane. So this whole group is removed. So here's the mechanism for that reaction. Step 1 is going to involve a proton transfer. Like many of the reactions we've been going over recently, lots of proton transfers. Reacts with hydroxide, take away one of those hydrogens. So this leaves me with a negatively charged nitrogen. Now there is a resonance structure here. I can move this bond to form a double bond between the nitrogens, and then a pair of electrons down to the carbon. And this is the form that's going to be reactive. In the next step. So both the nitrogens now have a neutral charge, but I have a carbanion. Right there. The carbanion will react with water to be protonated. And since we're in strongly basic conditions, right, we can protonate water to get hydroxide. Next step is going to be another proton transfer. Hydroxide will react with the other proton that's left on the nitrogen. All right, so at this point, what is the N2 beginning to look like? Nitrogen gas. One of the lone pairs can move down to form a triple bond, and then the carbon-nitrogen bond from the single bond will go to the carbon. So now, this is not an equilibrium step. I'm going to get a carbanion. Usually, this doesn't happen, right? A leaving group to give you a carbanion is something, when you first learn SN1, SN2, that's forbidden. You don't do that. But in this case, 1, we're in strongly basic conditions. But 2, and more importantly, nitrogen is, or N2, is a fantastic leaving group. Among the best leaving groups you can have. Because you're forming something that's very stable. N2 is very stable. It has no charge. And it's a gas. So it leaves the system, right? Anytime you produce a gas, which then leaves the system, that reaction is going to be driven forward. So that's how we can lose that N2 to give us the carbanion. The carbanion, also not in equilibrium, reacts with water to get protonated and give us our final product of pentane. So one note, this first step here, I didn't draw it as equilibrium, but you can go back and forth between protonating the OH group and then protonating the NH2 again. So it would probably be better to write this step as equilibrium as well. So the first 3 steps of the reaction, so 1, 2, and 3 are in equilibrium, and then steps 4 and 5 are not in equilibrium. Even step 5, which is a proton transfer, which usually that would be an equilibrium step, it's not here because you're protonating carbanion, which is, you're not going to now lose that hydrogen to form the carbanion again. because you don't have a leaving group like N2 to drive the formation of the carbanion.